Hi everybody, welcome to another video in Discrete Math, section 3.1 algorithms. Algorithm is a set of precise instructions for performing computation or solving problem. So in general, maybe solving a problem, not just for computers and others. And algorithm can be specified in different ways. Of course, you can describe how to do some things, or we do that in computer. We use the pseudocode. Now the difficult in this class that I cannot require programming because everybody using different might use different type of programming language, and of course I'm not a computer science person. I only know a few language, so I'm not familiar with what you are using. So in that case, it's difficult to assign prompts using programming. But my best advice in computer programming is if you can think as a computer, and that will help. Because that's simple, because we try to tell the computer to do something. If we can think as a computer, then it is easier. I remember when I took a test in computer science years ago, I write a computer program on a paper 2 pages long, and my teacher can look at that and tell that I missed one line, and so he certainly can do that. So that is amazing. We do computer science without computer. That is the next level for sure. Right. So some terminology in the algorithms of computer programming. We have input, what we put in, and the output is whatever values coming out of the computation or the algorithms. Correctness, an algorithm should produce the correct output. And finiteness, the program has to stop at some point, it cannot run forever. And effectiveness, it must be possible to perform each step correctly and at a finite amount of time. Of course, time is the resource, is very important. If we can produce the same result using less step, that would be much better, of course. And generality, the algorithm should work for all problems of the desired form. Right. For example, the first one we try to find the maximum. So try the maximum of a1, a2 to an. And so the rule here is first we say max is equal to a1. Now in computer science, from more common some common language, we use common some column equal, meaning we make a1 start to max. So this meaning that we take a1 store into the max. This is not equal to. If it is equal to, it is a logic statement. So we make a1 store to max, and then the rest is easy. We go from 2 to n, checking a2, a3, a4, and an. If it is bigger than the max, then the max will be equal to new values. So for example, if I have 1, 5, 3, and 4, first I say the max is equal to the first one, and then I compare that with the next one. The next step is 5 is bigger than that, so the new max is equal to 5. And then I'll take that compared to 3. Oh, that's not bigger, so the max still 5. Then you take max compared to 4. Well, that's still smaller, so the max is 5. So just whatever the bigger one, we replace that into the max, and then we just compare to the next one, and then the next one. So, and in computer program, pretty much any computer program, there is a loop that do something repeatedly, and there is the conditional statement, if and then. Of course, there may be other cases too, but there are two common code or two common tasks is a conditional, if something then do something, and then the second common is a loop to repeat the task, repeat do something where we change the index of the problem. Right. So that is the first most fundamental program of finding the maximum. Right. Next, searching algorithms. Searching is to find some certain things on a list. Right. And there are a few type of search. The first one is the linear search. So for example, the linear search, we have the input of x, so we're going to search for the values of x onto this list. And this time we use the while. So the difference between the while and the for is that for the for loop, it will go from 2 to n, so it will just keep going to n. The while loop is where something happened, it will do it. So the loop might be stopped until the while. It will keep doing things. If the condition met, it will just stop the loop. For example, I less than or equal to n, so it does go from 1 to n. And x is not equal to ai. So meaning that as long as each values here is not equal to the values we're looking for x, if we're looking for x, if we found it, we stop. We don't have to go to the rest of the list. I said we increase the index, and if it is still less than n, location is equal to I. If it is equal to n and we cannot find it, then the location is 0, meaning that if the location of the subscript of the term equal to x, if 0, if we do not find what it is. For example, if I have a list of 1, 2, 3, 2, 6, 3, something like that, and we look for 3, search for 3, and then it just, okay, is that the first one? Nope. Go to next one. Nope. Found it, and it will return the position is the third place. It stopped the loop. It will not go any further. If we go with this is much better. This should be the while loop and not the if or the for loop. If we use the for loop, we can just keep going and we can find it will stop at the last one. But since for the linear search is more efficient, if we found the values, we stop. We do not need to go any further. So yeah. So because if it is equal to, it will stop the loop. It will not go any further. Right. So like I said, this is the type of thing that we think like computer. Right. So that is the linear search. We just go through the list. If we found it, stop. Right. Next, it's called the binary search. The binary search is the search for the increasing order. Of course, similar thing can be done for the decreasing order. Right. So this algorithm compare the element to be found to the middle one. So it is in increasing order. So that's the key here. It has to be in increasing order. Now, if it is in increasing order, when we look, we just look for the binary search. We look for the first half or the second half. So compare with the highest of the first half. If the middle element is lower, then search the upper half. If it is not lower, search the lower half. So we divide that in half and compare with the middle one. If it is bigger than the middle one, search the upper half. If it is smaller than the middle one, search the lower half. And we just keep repeating, cutting the list into half and half and half until we find the position. So this is essentially what we do here. So we have 1 and n, that first and last, and then we'll compare that with the middle. And then if it is the case, we'll cut in half and cut in half. So that is called the binary search. So now let's think like a computer. Search 19 on the following list. Now, I said we try to think like a computer. So we have this list of numbers, of course, in increasing order. 1, 2, 3. Oh, let me see how many do we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So first we'll cut this in half. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. So cut this in half. Now, the algorithm is use the floor function. So 16 divided by 2 is 8. So we look at the 8 entry. Is 10. 19 is bigger than 10. So we have to look for the upper half. So we're going to look focus on this upper half. Because 19 is bigger than 10. Now, in this, we cut that in half. And we're going to look for this half or this half. And then the 19 compared to these values, it's bigger. So we will look for, in this particular, look for this half now. Now within that, right. There's a typo, there should be 19. Since 19 is not greater than 19, we're going to look for, if it's bigger, we look for the upper half. If not, look for the lower half. So we're going to look for this lower half. And that, for this lower half, we cut that in half again. And it's not in here, so it have to be in here. So now when we have only one single element, that's where it is. So it's going to binary search. Binary, so we cut that in half. If it is bigger than the one in the middle, we go to the upper half. If it is smaller than the one in the middle, we'll search the lower half. And they'll just pinpoint, just greater than. So if it is equal to, it is not greater than. So we search the lower half in that case. Alright, so that is searching. There are two of them. Of course, there may be more, but that's what we have. Just some example here. Now next is sorting. Sorting is put things in order, preferably, usually in increasing order. So that's how we sort a list. So there are two types of, we will study two types of sorting here. The first type is called a bubble sort. Right. So bubble sort is, I don't know why we come up with the bubble, but here the things. I just compare two elements. If it is in the right order, we keep it. If it's not, switch it. So we can pairwise entry here. Right. By the way, there's one thing I want to talk about. Is that from it will run to every entry to the list except the last one. And then of course we do j plus 1, so if up to n minus 1, then n minus 1 plus 1, so that up to n, so don't worry, we will have everything on the list. Alright, next, it just said we compare, and then of course we'll look at this in the next example. But for now, it said what I want to do is interchange. Let's say how can we perform interchange two values? The calculator, we cannot say interchange A and B. That's nice, but most computer programs don't have that. So we have to do the interchange like this. For example, I'm just look at an example here. As you have this cup, and then I draw a different cup. One cup have red, so let's say Y, and the other one has I said some kind of cocktail that is green. Right, now the task is how do we switch the red liquid into here and the green liquid over there. Right, so here things, we cannot just pull up together. We have to have a temporary cup. So if we're going to, first we're going to put all the red stuff in here, that stuff in here, so that cup will empty. And now we put all of this stuff there. So after that, of course, this cup will be empty. Yeah, so move there. And of course after that, we can put the red stuff in here. So I have to have the temporary cup to put one cup in there, so that will be empty, so we can swap place like that. So in general there will be this change. So first you're going to take the temporary cup equal to A. Computer program usually just semicolon at the end. That's the habit of mine. Right, so we take temporary equal to A, so we put that into A. Now A can be switched to something else. A therefore equal to B, because when we take something equal to A, so we can pull it out. Now it is empty, so ready to, if it is empty, you can make it to something else. Of course, we shouldn't say that empty in computer sense. We take temp equal to A, meaning the A is already duplicated. We have a copy of A in the form of temporary. So in that case, A can be something else. Because we already make a copy for A, we can change that to something else. And that change to B. Now, since we make a copy of B already, now B can be anything, and B is equal to temporary values. So the way I remember this is kind of cyclic. Temp to A to B, B to temp. Then just go in the cycle. Temp to A to B. I'm sorry. The backward. So we start A to temp, temporary to B, and then B. Right. Actually, I got them backwards. Right. Right. This is one step. Start A to temp, and then next B to A. That's the second step, and then temp start to B. That's the third step. So that's in a cycle. Temp to A to B, B to temp. Right, that. Right. So we have this example of showing the step of the bubble sort of this entry here. Right. So for this, say we go from I to 1 to n minus 1. Let's skip the last one here. And then next, for that, we're going to interchange from top to the bottom the consecutive entry. If the order is right, keep it. If not, swap. Sounds simple enough. Once again, think like computer. Next, more important, we swap the consecutive entry here. Right. Be a computer. Right. First, I equal to 1. So focus on that, and now we swap this because the order is wrong. And then this is the correct order, so we don't do anything. And so that will be 2, 3, 4, 1, 5. And now we check these two. Well, they're not the right order, so we have to interchange. We have to interchange. And the last one in the correct order, so we want to start. So that is when I equal to 1. Right. Next, so we're going to have this list. Now I equal to 2. Meaning we start from this. I equal to 2. When I equal to 2, actually, we always start from 1. But we're going to stop at the last one. We're not going to go to the last one, so we're going to stop here. Now, we check. Remember, the I, we go to 2, meaning that we're going to skip the last one. If n equal I equal to 3, we're going to skip the last 2. Alright. Now, when we compare the j, always compare the consecutive, so that's one good. That means the list is still the same. And then next we look at this too. Well, this need to interchange. And then next, this in the correct order. Remember, when I increase by 1, we're going to skip 1 at the bottom. So the bottom is correct order. We're not going to mess with that. So this is when I equal to 2. Now I equal to 3. We're going to skip the last 2. I'm going to copy the last result here. The last result. Sorry. Now this we will skip the last 2. Because every time we increase, we keep one more. Now we check. When we check, always check from the top. Right, this we need to interchange. Now let's check. That one's good. Now this 2. Right, so that's good. We don't need to check anything there. And that's it. We keep this 2. Yeah, no need to change there. So that is I equal to 3. Now I equal to 4. The last 3 will be good. But of course we already know that this is in the correct order. Right. We increase one more thing to keep. And we check. Oh, this is correct order already, so don't interchange. So we're going to do this. And it's good. Now, remember we go from 1 to n minus 1. There's 5 numbers, so n minus 1. So 4. We're going to stop, and we have the correct order. So that is called the bubble sort. Right. Next we call the insertion sort. We begin from the second element and compare the second with the first, and then put it before the first if it is not larger. So we compare the first 2, and then we add number 3, and then we try to put the 3 in the correct order. And then subsequently we just add one more and compare to the rest. Right, so that is the algorithm, a little more complicated. Right, for example, we try to order the same thing here. Now first we'll compare the first 2. So we put them in the correct order, 2 and 3. So that first 2 is correct. So this is correct. Next we compare that with the 4. We add one more, and those already correct order, so we're gonna keep this 3. Next we compare 2, 3, 4 and 1, see where the 1 need to be or need to place on first, so we're gonna keep that. And then next we keep with the 5. Is that in the correct order? If not, we put them in the right order of the all 5. So do this. Right. So pretty much compare the first 2, put in the correct order, then add one more, put in the correct order, all 3 of them, and then 4 and 5, so on, and that's what we have. So that is called the insertion sort. Next, the greedy algorithm. So the optimization problem of minimizing, optimizing some parameters over all the possible values. Among this is some example like finding a route between 2 cities with the smallest total mileage. So there's some example. I'm not going to do that with everything here. Optimization can be solved using the greedy algorithm, which will make the best choice for each step. And of course, that's not always guaranteed the best, but in some instance it does. Right, here's some example. Let's say we write the program to produce change using the least amount of corns. For example, if the change is 87, should not use that color, 87 cents. Right, so we say first to produce the least amount of corn, we have to use the biggest corn possible. Right, so let's use the quarters. Of course, we know that we can use 3 quarters. And after that, that's 75 cents, 87. And that gives it 12 cents. So 12 cents left. That's enough for dime. And of course that we have 2 cents left. 2 cents left, of course, is not enough for nickels, but enough for 2 pennies. Right, so this is something like that. Let's go to the greedy algorithm. Of course, we can write the program with this, no problem. And then another type program is develop the process that take an input, compute program along with its input, and determine the program will eventually hold with that output, with that input. So sometimes the good program should have this part in. So because if we enter the bad number, the program might be entered in a loop, and of course in that case it hold the computer, so it's not good. So we should write the program, it say that if it is in the infinite loop, get out of it. So that is called the holding problem. I'm just going to introduce the problem, but we're not going to write out all the little step here. Right, with that we finish section 3.1. As always, thank you for watching, and see you in another video in Discrete Math.